Welcome to the Explainer. Today, we're going to dig into a really fascinating question. Why can a simple physics puzzle, something a toddler could solve, completely stump some of our most advanced AIs? It reveals a huge gap in their understanding of the real world, a gap that's now sparking a revolution in what we call physical AI. Okay, so let's start with that simple test I mentioned. It's almost ridiculously easy for a person, but it shines a huge spotlight on a fundamental problem with even the smartest AIs we have right now.
So you look at this and you know the answer pretty much instantly, right? It's the ball on the curved ramp. Duh. It gets a steeper start, so it builds up speed way faster and just wins the race. It feels totally obvious to us. That's just, physical intuition.
But, and this is the crazy part, you ask a top-tier large language model the exact same question, and you get this super confident, very technical sounding, and completely wrong answer. It just doesn't get the nuance of how forces actually work over a path. This is that intuition gap. And it's exactly why we need a totally new kind of AI, one that doesn't just talk about physics, but one that actually understands it. So what makes this so difficult for an AI? Well, to really get why the new approach is such a breakthrough, we have to take a quick look back at the old, painfully slow way we've been trying to teach computers about physics for, like, the last 80 years. The old way, using what are called traditional solvers, is basically a brute force attack. You take a 3D model of something, let's say a car, and you have to break it down into this insanely complex web of millions, sometimes billions, of tiny little points. Then, the computer has to sit there and calculate all the physics for every single point, step by tiny step. Yeah, it is every bit as slow and agonizing as it sounds. And people have been doing it this way for ages. I mean, it goes all the way back to the 1940s with actual human calculators. Of course, now we have super fast GPUs, but the basic idea is the same. They all get stuck in that same fundamental bottleneck, this slow, one-step-at-a-time process that costs a fortune in time and computing power. But now, something really cool is happening. A completely new approach is just smashing through that bottleneck. And it's not about calculating faster. It's about thinking differently. We're talking a total paradigm shift. So instead of grinding through the physics from scratch every single time, a new hero has entered the chat. The Generative Physical Engine. You can just call it Physics AI. And it basically throws that whole slow, step-by-step method right out the window. Let me put it this way. These new engines don't calculate, they generate. They're trained on mountains and mountains of simulation data, so they start to develop their own kind of intuition for physics. So instead of slogging through all the intermediate steps, they can just look at the starting point and bam, jump straight to the final outcome. They're not doing the math, they're predicting the answer based on what they've learned. And the result of this? Well, it isn't just a little bit better. It is an absolute revolution in speed and in what's even possible. Just look at that number. 1,000 times faster. On average. That's not an incremental improvement. That's a whole new world. We're talking about tasks that used to take days, now getting done in just a few minutes. It's incredible. So what does this actually look like in the real world? Well, in aerospace, it means you can test hundreds of new designs in the time it used to take to test just one. Think about that. Some companies are seeing speedups of over 300 times, cutting down simulation times from a whole week to just 30 minutes. And it's just as big a deal in Hollywood and in architecture. Visual effects artists can now create perfectly realistic fire, smoke, and water in real time. No more waiting days for a render to finish. Architects can see instantly how a new skyscraper is going to affect wind patterns in a city, letting them design better, safer spaces right from the start. And for climate scientists, this is a total game changer. It means they can run these huge sets of weather models to get way, way better at predicting extreme events like hurricanes. This could fundamentally change how we prepare for disasters and literally save lives. So here's the real kicker. This incredible speed isn't just about making cooler movies or faster race cars. The true purpose here is to create the training ground for the entire next generation of AI. Because the ultimate goal, the holy grail, is to create what we call physical AI. You can think of it as the brain for a robot, an AI that can safely and effectively see, plan, and act in our messy, complicated physical world. But there's a massive roadblock. Unlike language models, which had the entire internet to learn from, there just isn't a giant database of how physical things are supposed to interact. You can't just download it. That data has to be created from scratch. And that is where these new generative physical engines come in. they're the heart of this three-part system. First, you have a simulation computer that uses these engines to generate just tons and tons of realistic physics data in a virtual world. Second, you have an AI factory that uses all that data to train the brain of the physical AI. And then third, you put that trained brain into a robot computer and let it run in the real world.
So this all brings us to the future. Because, look, this technology is absolutely revolutionary, no doubt about it. But there are still some major hurdles we need to clear before we have helpful, autonomous robots wandering around our homes and offices.
The two biggest challenges right now are what we call generalization and trust. AIs are fantastic when they see things that are kind of like their training data, but they can get really confused by totally new situations. And then there's trust. I mean, before you let an AI design the wing for a plane that you're going to fly on, you need to know exactly how sure it is about its answer. We need AIs that can tell us, hey, I'm 99.9% sure about this. Or, you know what, this is a weird one, I'm only 50% confident.
And believe me, the motivation to solve these problems is just massive. The market for generative AI is predicted to explode, from around $40 billion today to nearly $900 billion by 2032. Physical AI is a huge chunk of that pie. Whoever cracks these challenges is going to define the next decade of technology. Which leaves us with one last kind of mind-blowing thought to chew on. We started all of this by trying to teach AI our understanding of physics. But what if, just by learning the deep patterns of the universe from raw data, these systems could one day show us fundamental laws of physics that we never even knew existed? Now that's the truly revolutionary promise of physical AI.